So the greatest common divisor of two numbers will be the greatest common divisor of a sequence of remainders formed by successive divisions, where every divisor becomes the next dividend, and every remainder becomes the next divisor. If a divided by b is q with remainder r, then the greatest common divisor of a and b is the greatest common divisor of b and r. So for example, if we want to find the greatest common divisor of these two numbers, we'll divide, the divisor becomes a new dividend, the remainder becomes a new divisor, and we'll repeat. Divisor becomes new dividend, remainder becomes new divisor, and we find, and again, and continue, until we get a remainder of 0, at which point we can no longer divide. So our theorem says that our greatest common divisor of the original numbers is going to be, and since any number divides 0, the greatest common divisor will be the largest number that also divides 17, which is going to be 17, and so our greatest common divisor is 17. Since the last remainder will always be 0, and the greatest common divisor of any number in 0 is just going to be whatever that number is, this means that the greatest common divisor will be the last non-zero remainder. And this gives us the Euclidean algorithm for finding the greatest common divisor of two numbers. Or does it? Remember, an algorithm must terminate after a finite sequence of steps and always produce an answer. Since we claim this is an algorithm, it has to terminate after a finite number of steps. Now, note that we're finding quotients and remainders repeatedly. Since R1 is the remainder from A divided by B, then B has to be greater than R1. And since R2 is the remainder from B divided by R1, then the remainder has to be less than the divisor. And likewise for R3. And so B has to be greater than the first remainder, which has to be greater than the second, which has to be greater than the third, and so on, which is a descending sequence of whole numbers, which must have a last non-zero entry, which we'll call Rn. Now, why would Rn be the last non-zero entry? Well, note that if it's not 0, we can divide by it to obtain one more step. Since we're assuming Rn is the last non-zero entry, then the remainder after it must be 0. And the claim is the last non-zero remainder is the greatest common divisor. Now our lemma tells us that we have this chain of greatest common divisors, and again, since any number divides 0, the greatest common divisor of Rn and 0 will be Rn. And so Rn is the greatest common divisor of A and B. At this point, it's useful to remember, prove it again. If you really want to understand mathematics, take any theorem and find multiple proofs with different approaches. We found an easy proof using the lemma that if A divided by B is Q with remainder R, then the greatest common divisor of A and B is the greatest common divisor of B and R. But let's try to prove it without the lemma. We'll use induction on the number of steps. First, note that if R1 equals 0, then A divided by B is Q1, and so B is the greatest common divisor. We'll regard this as a trivial case and ignore it. Remember, you can ignore anything you want, as long as you're explicit about it. Now let D be the greatest common divisor of A and B, and suppose the Euclidean algorithm terminates after one step, so that first remainder is the last non-zero remainder. So by assumption, the Euclidean algorithm terminates after one step, and so we have A divided by B equals Q1 remainder R1, And then in our next step, when we divide by R1, we get a remainder of 0. Now, since D divides A and D divides B, then D must also divide R1. So D must be less than or equal to R1. But since B divided by R1 is Q2, then we know B is R1 Q2, so we know that R1 divides B. And since our first quotient gave us A equals Q1B plus R1, then we know that R1 has to divide A as well. Consequently, R1 is a common divisor of A and B, so R1 has to be less than or equal to the greatest common divisor. In other words, R1 has to be less than D. Well, since D is less than or equal to R1, and R1 is less than or equal to D, then R1 has to be equal to D, which establishes the base step that the remainder, if we stop after one step, is the greatest common divisor. Now suppose that if the Euclidean algorithm terminates after n equals k steps, the last non-zero remainder rk is the greatest common divisor. Now consider A and B where the Euclidean algorithm terminates after k plus 1 steps. So we have A divided by B is some quotient with remainder, B divided by R1 is some quotient with remainder, and so on, with rk plus 1 being the last non-zero remainder. So if we divide by it, we get some quotient with a remainder of 0. Notice that the last k steps are identical to those we'd use to find the greatest common divisor of B and R1. And so rk plus 1, by our reduction hypothesis, has to be the greatest common divisor of B and R1. So let D be the greatest common divisor of A and B. So as before, D has to divide R1, so D is less than or equal to R1. Again, since rk plus 1 is the greatest common divisor of B and R1, then rk plus 1 has to divide A as well, and so rk plus 1 must be less than or equal to D. Consequently, we'd like to be able to compare D and rk plus 1, but the obvious steps don't allow it. So we should see if we can make a connection between the two. So if D divides A and B, then we know that D divides R1. But in our second step we have, and since D divides B and R1, it must also divide R2, which suggests that D divides R3, R4, and so on, which we can prove by induction, but we'll let you do that. So D does divide rk plus 1, and so D is less than or equal to rk plus 1. And since rk plus 1 must be less than or equal to D, and D must be less than or equal to rk plus 1, then D must equal rk plus 1, proving the induction step, and so our Euclidean algorithm is an algorithm. It will always terminate after a finite number of steps, and it will always give us the greatest common divisor.